make like factorization theorem for forward scattering amplitude using perturbative insertion of the Glauber Lagrangian, and we're going to derive a factorization theorem of the following form, where the forward scattering amplitude is going to be a convolution of a soft piece and two collinear p's on the n and the n bar direction. Then I'm going to study the rapidity renormalization group for the soft piece, and we're going to see how then we can get a BFKL equation from this rapidity renormalization group. And if I have time, like briefly at the end, I'm going to see how we can get a BFKL equation also for Cn and Cn bar using consistency. So just like to give a very brief introduction about what's BFKL, if someone doesn't know about that. So the idea is that the BFKL equation is summing log of x, where x is roughly the ratio between the t minus the sum invariant and s. So in the limit where this guy is much less than 1, I'm going to have like logs of x that I want to resum. And to give an analogy to something that we have already seen in class, we can consider, let's say, just like a gluon-initiated process. It could be like LHC, Higgs production at the LHC and a point like approximation. In general, we know that we can have some sort of radiation from the initial state legs. And if we label with like 1 minus x and x, the fraction of the initial energy that is going into the hard scattering or in the radiation, we have two opposite situations. One is the 1 minus x much smaller than 1. So when the radiation is almost soft, so that this is called the threshold limit. And then we have exactly the opposite case. When the radiation is carrying out most of the energy, then we have x much smaller than 1, and this is called the RRG limit. And so we can see that if this energy is quite small, we can actually see this as almost a forward scattering process, and so that's why like the RRG limit is typically connected to the forward scattering amplitude. Okay, and as we have seen in the last lecture in class, forward scattering processes are mediated by the Glauber Lagrangian in SCET, and so the problem here is that okay, the Glauber Lagrangian is coupling soft and collinear modes, so at leading power, so we can actually cannot factorize the modes. So how can we prove factorization theorems in this framework if like the process is mainly mediated by factorization violating Lagrangian? And the approach that we're going to follow is almost the same that you typically use when you have to deal with subleading power Lagrangian SCET, because we know that soft and collinear modes are decoupling via the BPS feeder definition, just a leading power. So to do SCET as subleading power, you typically insert perturbatively this factorization violating Lagrangian, and we're going to follow the same approach here. And so basically, the idea is that I can take like the generic time evolution operator in SCET, and this is going to be something like path integral of the exponential of both the usual SCET Lagrangian, so C like n bar s of x, plus the leading power Glauber Lagrangian. And so this piece is the usual SCET leading power Lagrangian. So this doesn't violate factorization. While this is the problematic piece, and this is the one that is violating violates factorization, of course, of soft and collinear modes. So the idea is try to keep at all orders the evolution in the like non-violating piece, and try to insert perturbatively the violating part. And in order to, so like naively, the idea is to expand the Glauber contribution, which is something like the exponential of so 1 plus I for x g of 0 plus at higher powers I get minus 1/2 and t products of d4 x1 d4 x2 of 2 insertions x1 g0 plus dot 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 plus higher terms. So the problem here is that actually, okay, what are we expanding in? I mean, we don't have like a power counting parameter telling us that this term is subleading with respect to this one. We can not even talk about expansion in alpha s, because actually these Lagrangians contains terms at all orders in alpha s. So the organization of this expansion is actually kind of tricky. And in order to organize that in a sensible way, we need to know something about LG. And basically, the first goal that we want to achieve is instead of producing a factorization theorem that is valid at all orders in everything, we just want to have like a factorization theorem that is at least enough to resum leading log, like in the leading log approximation. And so in order to do that, as I was saying, we need to know something about what's the structure of LG. And the Glauber Lagrangian is made by two main pieces. One is the so-called like 3 rapidity operators, which is known as AB, because it is explicitly dealing together with the soft and bar, plus just a 2 rapidity piece. And now with this structure, we now try to start thinking about okay, can we actually drop like higher insertions? And the answer is no, because for example, we can see that the quantum numbers of these operators are in principle the same as the t product of two of these ones with one n and n bar. So in general, we can expect, and actually this is the case, that this 3 rapidity sector operator mixes with a t product of 2 of these guys. So like ONA 1 over pt square, OSA, and the same guy with OSB and bar. And actually, this is the case. So, so in this expansion, it would be extremely problematic to drop those terms, because now on the renormalization group, these terms can talk to each other, and so if we drop this, we wouldn't close the RG. So, but from this observation, we can actually see, we can get like an advice or how to proceed. And what we can observe is that the t product of these two operators and this single operator actually have the same number of n and n bar operators. So probably like the good way to to set up this expansion is to organize not by the number of LG insertion, but the number of n and n bar operators that are appearing. So so let's set up this in the following way. We can write like this t exponential of like the integral of LG is basically 1 plus the sum of k prime, where k counts the number of ONS, and k prime counts the number of ON bar S. So more explicitly, what would UKK look like? K prime look like? Gonna be something like so T product of what? So this is counting the number of ON operators. So a product for I goes from 1 to k of n of some AI. This guy brings some color index times a soft operator that is gluing the ON and the ON bar, the n and the n bar sector, and this is gonna have like all the color indices, so from A1 to AK, and then k prime color indices from the other sector, so B k prime, and we just label this in the same way as the overall momentum, times the same idea on the other side. So like J goes from 1 to k prime, the product of k prime ON bar operator, so B J. And okay, so the first non-trivial term of this series is going to be 1, 1. So when I just get one operator on each side, and this is going to be something like an A, and so S A B, sorry, 1, 1 on bar B, where the soft operator that is gluing these two ON and ON bar is going to be so S11 AB. Is it going to contain both contribution from a single insertion and also from a T product of two insertions? That's exactly related to this argument I was making before. So this is going to be something that goes like ABS plus the T product of OS A, OS B. Okay? So now, in this way, it's like the good way to organize this expansion, and we see that is not exactly an expansion in the number of insertion of LG, but is something like a little bit more involved. And now this guy is closed under the renormalization group, because now the mixing between these two guys stays in the same operator. So now we want to study with this setup, we can now study a forward scattering process. Let's say take P, something happening in the middle, P prime, where this is in the n direction, this is in the n bar direction. And I want to study this process at lowest order in UKK, KK prime. see if I can find a better chalk. And this means if I express T11, because I mean in general this can get contribution from all decay. I label 1,1 the one that is at lower order in UKK. This is basically the sum over like the intermediate states of PP prime U11 X U11 dagger PP prime, and now I can factorize this expression in the following way. I can factorize X in a n collinear, n bar collinear, and a soft piece, and let these states evolve just with this non-violating Lagrangian. Since I've factorized since I've explicitly inserted the contribution from the Glauber Lagrangian. So basically now I can, I mean, there is like a bit of algebra, but the idea is that now I can rewrite this as a convolution, like in the perp momenta, of SG. Sorry. So I have like a collinear function. As I was saying in the outline, I'm going to have like a collinear function, a soft function. It depends on two perpendicular momenta, one coming from the n direction, the other related to the n bar direction. And where these functions are basically the matrix element of like pictorially what happens. I have n bar, and some soft guy. So basically I get something like Cn some soft interaction, and then P prime with a Cn bar, which is related to this evolution. And so the actual expression of these functions is going to be something like I mean, the point is that here you have like the n piece, the n operators, the soft operator, and the collinear operator. So I'm going to take a matrix element of these single guys with P or P prime, this with the vacuum. And so basically what I'm going to get is something like P on chi n, because now I can factorize this, so sum over x con n bar x soft, P, and this is this guy, times matrix element of S, and the soft operator is S11. Times the same discussion that I've done here in the n bind direction, now between P and P prime states. So this is the factorization theorem, and now let's try to this is like the bare factorization theorem. We can actually promote this with like the instead of the bare functions to have like the renormalized functions. And so in general, all these guys are going to depend on some rapidity scale nu. And by studying the rapidity renormalization group of this object, we can try to resum the logs that are coming from the fact that the soft guy wants to stay at a different scale with respect to the collinear guy. Typically, this is going to be roughly with mu as order of minus t, while these the logs that are coming from one loop calculation are going to have like get minimized when I set nc of the order of square root of s, which is basically p minus. And okay, so the one loop, let's start by say, okay, we set the overall scale at the collinear scale, so these two guys don't run, and we need to study only the renormalization group for the soft function. So let me try to draw in picture the renormalization of SG. I think I can remove everything here. Good. So at least I didn't. So just like we want to study this guy, where this one is exactly this one. Okay. So in picture, SG is going to have a 3-level contribution. So this is basically the matrix element between the vacuum and some soft state. At 3 level, I can pick just so from here, I can have like a 2 contribution, and as I've written there, the operators are actually coming. So OS AB versus OS A, they have like the same power in alpha S, but since here I need a T product, this is order alpha S square at first, and this starts at order alpha S. So at 3 level, I just have 2 insertions, 2 contribution just from OS AB on the 2 sides of the cut. So just let me write down OS AB on the other side, in principle OS A prime B prime. Then at 1 loop, so this is the 3 level. At 1 loop, I can have like many things. I can have the T product of let's start from the fact that OS AB contains a higher number of gluons Feynman rule. So this has a 0, 1, 2, 3, infinite gluons emission. And the first one is also known in literature as the Lipatov vertex. So basically, the 1 gluon emission from ABS is known as the Lipatov vertex, and I can glue that with the same guy on the other side of the cut, OS A prime B prime. And this is, since I have a gluon crossing the cut, this is the real emission diagram. But now I can also have, from the T product, virtual corrections. In particular, the OS, as I've written here, has both 2 quarks, or like 2 gluon Feynman rule. So I can have, let me just write down the gluon 1. So I can have OS G A with like 2 soft gluons, the T product of the same operator G B on the other side. And of course, on the other side of the cut, actually I get still like the 3-level contribution. Plus the same guy with the quark loop. Don't let me avoid to write that down. And then I can also have, since I can have the two gluon Feynman rule from OS AB, I can have a self-contraction of OS AB. And so those are virtual diagrams. And actually, you can show that these are the only ones contributing at leading log to the rapidity renormalization group, because the quark one has no rapidity divergences. And so let me write down the result when we so in order to compute these diagrams, those are going to be rapidity divergent. So you need a rapidity regulator, as we've seen in class. So that part is not actually changing. And the result is that SG bare depends in general on Q perp and Q per prime, which is actually like the momentum that is routed out of these vertices. And at this order, actually, there is a delta function between both the colors, because we're in a color singlet state, and in the momenta. So actually, Q bar, Q perp, Q per prime here are the same as, let's say, Q perp second, Q perp fourth in the other direction. So basically, the SG depends only on these two variables. And so this is actually equal to the 3-level one, so SG 0. Plus alpha S correction, that is going to be something like alpha S, there's a CA, a P square. And here I'm keeping only the leading pole in 1 over eta. So because I get like a gamma function of eta alpha. I mean, eta is the analog of epsilon in the rapidity renormalization group. And then I get actually a convolution in the perp. So SG plus so basically this is coming from the real radiation, depends in general on K perp, that is K is here is the momentum of the gluon crossing the cut. And so this is perp square. Minutes, great. Okay, and now I can use this wonderful color stuff to try to match. So this one is giving you this term. This one is giving you these two terms, and this one is giving you this term. So actually, there is a partial cancellation between this diagram and this diagram. So this one goes away, and this one goes away. I just get a minus 1/2. So in this way, I get I can get so this is like the Baire function from the expression of the Baire function. I have a 1 over epsilon pole. I need a constant term to cancel that. And so I basically get SG renormalized equal to Okay, and so basically I have a convolution in the renormalization to get like the Baire function, and sorry, to get the renormalized function. And so from this expression, you can imagine that I'm going to get a renormalization group equation that is also a convolution. And so this is a nice example, because of course the Baire Lagrangian, soft function at all orders does not depend on nu, so I can actually I can derive an RG equation for the renormalized one, and this is basically mu d nu dsg renormalized, really. Now, just let me write this down as and where the anomalous dimension is coming from like the usual expression that we have seen also in class for the relation between the counter term and the anomalous dimension in the case of a convolution structure like this. And so that when we basically now we have all the ingredients because we can compute the from this expression we can compute this guy. From this guy, we can compute the anomalous dimension, and the anomalous dimension is the key ingredient is going to evolve. I can then solve this equation in nu for the normalization, the renormalized soft function, and get the all order. This is like an all order result in the like soft and collinear emissions, and then I can resum all the logs. At this point of nu. So just let me write down the final result. By doing this procedure, I get the BFKL equation for SG, that is so nu CA alpha s p square. Okay, so this is a nice example, like a different example, or like a more complicated example of what we have seen in class, because this is like just like combining all the pieces. We have a renormalization, rapidity renormalization group equation, which is involving also convolution. So that's actually something that we haven't seen in lecture, but is conceptually. Follows the same steps as we have seen for the invariant mass renormalization group evolution. Thank you very much.